going to use a process similar to what we did at the very beginning of the semester when we talked about how do we solve equations that have fractions in it. We learned that we can multiply every single term by the least common denominator to clear or cancel out or get rid of the fractions. And that's exactly what we're going to do here. The other difference is with rational equations, when you have x's in the denominator, you do have to check your answers. And by that I mean you have to make sure that you don't get any zeros in the denominator. We learned that we're not allowed to divide by 0. So if the answer gives us a 0 in the denominator, it actually doesn't work. We say it's an extraneous solution. So let's take a look at a couple of examples. In example 1a, let's see, we've got denominators of 3x and x, and that means my LCD is going to be 3x. So I'm going to take every single term of the equation. I'll just rewrite my equation down here. So all three terms, and I'm going to multiply those by 3x. 3x over 1, 3x over 1, even the 10, even things that aren't fractions. So when I multiply everything by 3x in this first term, the 3x's cancel out, and I'm just left with 2. In the second term, it's the x's that cancel, and now I'm left with 3. And then 10 times 3x is 30x. And now all of a sudden I have an equation that I can solve. I know that 2 plus 3 is 5. So 5 is 30x. We can divide both sides by 30. And so we get this fraction 5 over 30, which reduces to 1/6. Now, we do have to make sure that this denominator is not going to give us any zeros, or this answer is not going to give us any zeros in the denominator. And if you plug 1/6 in for x, it doesn't really matter what you get. The important thing is I can see that I'm not going to get zeros. The only way I would get zeros in the denominator is if x was 0. And that's not what happened. My answer is 1/6. All right, example 1b. So my denominators here are x plus 2. And so that means my least common denominator is just x plus 2. So I'm going to take this equation and multiply everything by x plus 2. So I just copied down the equation so it's a little bit bigger. And I'm going to have to multiply the 1 by x plus 2. Okay, so I'm multiplying the 1 by x plus 2, the second fraction by x plus 2, and then the right-hand side by x plus 2 as well. So 1 times x plus 2 is just x plus 2. And then this second fraction, the x plus 2's are going to cancel, and we are just left with the 3x. And then on the right-hand side, something similar happens. The x plus 2's cancel, and we're just left with the -6. All right, so this is something we can solve. If I combine like terms, I get 4x plus 2 equals -6. Minus the 2, so 4x equals -8. Divide by 4, x equals -2. Now, it's tempting to just stop x equals -2, but as I said earlier, you do have to check your answer. And what I mean by that is the thing you have to check is if you look at those denominators and you put that answer in, you have to check and see if you get 0. It's fine to do the check in your head if you want. I'll write down what I'm doing. So if I plug -2 into x plus 2, I get 0. And we cannot have 0 in the denominator. So that tells me -2 is not a solution. And that means this equation has no solution. So again, we clear the fractions, we solve, but if we happen to get a number that when we plug into the denominators gives us 0, then we have to cross it out. It actually doesn't work. All right, let's do one more example. I'm going to copy down this equation, 3 over x minus 5 plus 1 over x minus 5. And with that right-hand side, I'm going to write my denominator in factored form, x plus 5, x minus 5. So having that denominator in factored form helps me figure out what is the LCD. I have denominators of x minus 5, and then I have this x plus 5, x minus 5. So my LCD needs an x minus 5, and it also needs an x plus 5. So I'm going to go through and multiply everything by that LCD x plus 5, x minus 5. And then once again, things should cancel. So first term, the x minus 5's cancel, and I'm left with 3 times x plus 5. Second term, again, the x minus 5's cancel, so I've got 1 times x plus 5. And then on the right-hand side, everything cancels, and we're just left with that too. So I'm going to get rid of parentheses. This is a 3x plus 15 plus x plus 5 equals 2. Combine like terms. 4x plus 20 equals 2. Minus the 20. So 4x is minus 18. And then if I divide by 4, let's see, 18 divided by 4, that's a negative 9 over 2, or negative 4.5. Does that give me 0? Well, the only things that would give me 0 in the denominators are 5 and negative 5. And so since I didn't get those, my answer is negative 9/2. Now we can use this same process if we want to solve a formula for a specified variable. So for example, we're going to solve the formula c over b plus h equals a for h. So first thing I'm going to do is multiply everything by the denominator, or the least common denominator, to get rid of the fractions. So in this case, that just means I multiply both sides by b plus h. On the left, the b plus h's cancel, and I'm just left with the c. And then on the right, I've got an a times b plus a times h. Now that we don't have fractions, it might be a little bit easier to get the h by itself. So I would start by minusing the ab. So now we've got c minus ab equals ah. And then to finish, we just have to divide by a. And that's our final answer. H equals c minus ab all over a. And I'm just going to leave the answer like that. Note, you cannot cancel those a's out because it's not a common factor. There's no GCF. There's no factoring you can do. And so that's how I know I can't cancel anything. So same process for part B. I'm going to multiply both sides by p because that's the denominator. In other words, that's the least common denominator. So I multiply both sides by p. The p's are going to cancel on the right. So now mp equals 2v squared. What are we solving for? We are solving for p. So all I have to do now is divide by m. And that's it. My answer is p is 2v squared divided by m. So this process works whether you have equations with x's or formulas. The idea that if you have an equation with a fraction, you can multiply everything by that denominator, and that lets you get rid of the fractions. So finally, we're going to take a look at two different types of application problems that involve rational expressions. The first one is a work problem, and the second type is a motion problem. And so I'm going to start by just kind of explaining the work problem, and then eventually I'll give you kind of a pattern or a formula. And so if you don't want to write down this first part, that's okay. I am going to do some erasing and then eventually write down a formula. So the concept is, so Joey is building an engine, and Aaron is building an engine, and alone, it takes them a long time to build the engine. But if they work together, they can get the job done faster. And so the basic idea is, just imagine, so this is just an aside to set it up. Let's say it takes someone 10 hours to complete a task. Okay, whether that task is building an engine or mowing the lawn, whatever it is. If it takes 10 hours to complete the job, that means in 1 hour, you should be able to get 1/10 of the job done, right? And then in 2 hours, you should be able to get 2/10 of the job done. So in X hours, we should be able to get X/10 of the job done. And so that's kind of the idea that we're going to use to build our equation. That each person alone can complete a fraction of the job, and together they're going to complete the entire job. Okay, so let's erase that, and now let's get the problem started. So basically, the pattern that we're going to use is in these problems, we'll say that the time they spent together divided by the time it takes person number 1 is basically going to be the fraction of the job that the first person can complete plus the time they spend together divided by the time it takes person number 2. That's going to be the fraction of the job that the second person can complete. And the idea is we want to figure out when is this going to equal 1, because the 2 people are trying to complete one engine or one job. So each person does a fraction of the job, and altogether they keep working until one job is complete. So this is kind of the pattern that we can use for these work problems. I know that was a fast explanation. There's a little bit more in your textbook in section 7.5, or I can go over that a little bit more slowly for someone who wants a little bit more background, give you a little bit more detail. But basically in this problem, it says it takes Joey 9 hours longer than Aaron to rebuild an engine. Working together, they can do the job in 20 hours. How long does it take each of them to complete the job alone? Okay, so I don't know how long it's going to take Aaron. I don't know how long it's going to take Joey. I do know that together, it'll take them 20 hours. So I'm going to put X in for Aaron because I don't know how long it takes her. And if it takes Joey 9 hours longer, I'm going to call him X plus 9. So these are my 2 people and the time it takes them together. And I can plug that into the formula I just gave you. So together is 20. We'll say person 1 is X. Together is 20. Joey is X plus 9. We want to know when does that equal 1. So the idea is the first fraction is the amount of the engine Aaron will be completing. The second one is the amount of the engine that Joey will be completing. We're going to keep working until that adds up to 1. So here's a rational equation. To solve, I'm going to find the least common denominator. So my denominators are X and X plus 9. That means I'm going to multiply everything in this equation by X plus 9. All 3 terms. So I'm going to try to do the canceling in my head. First term, 20 over X times X plus 9. It's the X's that cancel. And so I'm just going to be left with 20 and the X plus 9. In the second term, now the X plus 9's cancel. So I just have 20X left. Equals, let's see, nothing cancels. So that's X plus 9. So there's my equation. It doesn't have any fractions. I'm going to get rid of parentheses, so distribute the 20. And then I'll distribute the X on the right-hand side. I'm going to combine like terms. And this equation now, unlike the other ones, is actually a quadratic equation. It has an X squared. So there's the squared. So anytime we have a quadratic equation, to solve it, we have to set one side equal to 0. I really like it when the X squareds are positive. So I'm actually going to subtract everything on the left and move that over to the right-hand side. So I'll have that positive X squared. So now I've got 0 equals X squared minus 31X minus 180. And so we're going to see if we can factor this thing. So we need product of 180, sum of negative 31. So I just went through and made a list and figured out, well, what can I divide 180 by? And once I got to this 5 and 36, I think that is going to work out if I make the 36 negative and the 5 positive. So if x minus 36 equals 0, x could equal 36. If x plus 5 equals 0, x equals negative 5. Now, negative 5 doesn't make sense in this problem. We're not going to have a negative time to complete a task. So 36 must be the answer. And so I guess that's Aaron's time. So it takes Aaron 36 hours. And so then for Joey, it takes him x plus 9. So 36 plus 9 is 45 hours. So it takes them much longer if they work alone. And that kind of makes sense then. If they work together, they can get the job done much faster in 20 hours. All right, the second type of application that you might see will be a motion problem. We've dealt with some of these in the past, and we use this distance equals rate times time relationship. And we'll use the same relationship here. So let's read the problem first. It says the speed of the current, so the water is 3 miles per hour. Sean can kayak 4 miles upstream in the same amount of time it takes him to go 10 miles downstream. How fast can he kayak in still water? So the thing we're solving for, the x, is going to be Sean's speed in still water, or Sean's speed without the current. So we've got two cases. We've got the upstream and the downstream case. Let's see if we can complete our table for those two cases. So it says 4 miles upstream, and then we know 10 miles downstream. When he's going upstream, that means the water is going in the opposite direction of him. So he's paddling at speed x, and the water is slowing him down at 3 miles per hour. So his rate is going to be x minus 3. Whereas when you go downstream, you're going in the same direction as the water. He paddles at rate x. Now the water actually makes him go faster. So x plus 3 will be his speed downstream. Now, we don't actually know anything about the times, other than the two times are going to be equal. And so here's where we're going to use our relationship to fill out the time column. So if distance equals rate times time, then if we divide both sides by r, we get an equation for time. Time is distance divided by r. So that means the time upstream would be 4 divided by x minus 3. And the time downstream would be the distance 10 divided by x plus 3. So we got our time using this relationship right here. Time is always going to be distance divided by speed. All right, so finally, this is a lot of work just setting it up. The last piece of information we haven't used is this problem is telling us this is the same amount of time. It takes him the same amount of time to do both of these trips. And so what that means is we can just set our two times equal. 4 over x minus 3 has to equal 10 over x plus 3. And now this is an equation we can solve. I can multiply both sides by that LCD, which would be x plus 3, x minus 3. And so then on the left-hand side, my x minus 3's cancel. So I get 4x plus 3. On the right-hand side, the x plus 3's cancel. So 10 times x minus 3. And this is something we can solve. We get rid of the parentheses. And then we need all the x's on one side. I put the x's on the right this time. So 12 is 6x minus 30. I add the 30. So 42 equals 6x. Divide both sides by 6, so it looks like x is 7 miles per hour. So these are the two types of applications you're going to see in this section. And you've got a formula for the work problems. And for the motion problems, you can use this table. And remember that the time is always going to be distance divided by rate. I know there's a lot in this lesson. It is one of our longer lessons, so please talk to me or the tutors if something didn't make sense.